Today's lecture explains how advanced water recycling converts used water into a resource suitable for carefully defined purposes. The exact treatment train varies according to the incoming water and the quality required at the end. Water intended for irrigation may need a different standard from water entering an industrial system or supplementing a drinking water supply. Nevertheless, most facilities use several barriers in sequence rather than relying on one method. Each barrier targets particular materials, and later stages protect against anything that passed through earlier treatment. We will follow the water from its arrival at the plant to final storage and quality control. The first stage is preliminary treatment. Incoming wastewater may contain cloth, wipes, plastic, wood, and other objects that could block pipes or damage equipment. The flow therefore passes through metal screens with openings designed to trap these large materials. Coarse bars remove the largest objects, and finer openings may follow to capture smaller pieces. Mechanical rakes clean the trapped material from the bars so that water can continue moving. The removed material is washed, compacted, and disposed of separately. It does not become part of the recycled water. Screening protects pumps and valves, but it does not remove dissolved pollution or very small suspended particles. After this, the flow enters a chamber where velocity is carefully controlled. Heavy mineral material such as sand and grit settles while lighter organic particles remain in motion. Removing this abrasive material reduces wear on pumps and prevents deposits from accumulating in later tanks. If the flow moves too quickly, the mineral particles remain suspended. If it moves too slowly, useful organic material may settle with them. Operators therefore adjust channel dimensions, aeration, or mechanical movement to maintain the required conditions. The water is now ready for primary treatment. It enters a large settling basin where movement becomes slow and relatively calm. Suspended solids that are denser than water sink through sedimentation and form a layer of sludge on the bottom. Oils and grease may rise to the surface and are removed by a separate skimming mechanism. Rotating scrapers move settled sludge toward a collection point without disturbing the entire basin. Primary treatment removes a substantial part of the suspended material, but much dissolved organic matter remains. This dissolved material requires biological treatment. The water enters an aeration tank containing a managed community of microorganisms. Blowers or mechanical devices transfer air into the liquid and keep the contents mixed. The purpose of this air supply is to provide oxygen for aerobic biological activity. The equipment also prevents the biological solids from settling too early. Supplying more air than necessary wastes electricity, while insufficient supply slows treatment and may create unpleasant conditions. Sensors help operators maintain an appropriate concentration under changing flow and temperature. Naturally occurring bacteria consume dissolved and very fine organic material as a source of energy and growth. They convert part of it into carbon dioxide, water, and additional biological cells. Other microorganisms contribute by breaking down particular compounds or transforming nitrogen. The biological community is effective only when temperature, acidity, oxygen supply, nutrients, and toxic substances remain within acceptable limits. A sudden industrial discharge can disturb the community, which is why control of incoming waste remains important. Following aeration, the mixture usually enters a secondary settling basin. Biological solids settle and are partly returned to the aeration tank to maintain an active population. Excess material is removed for separate treatment, which may include thickening, digestion, and dewatering. At this point the liquid is much cleaner, but advanced recycling requires additional barriers. One option is filtration through granular material, yet many modern plants use membrane systems. Membranes contain extremely small openings that allow water through while retaining fine particles and many microorganisms. Pressure or suction drives the water across the barrier. The surface gradually becomes coated, so regular backwashing and periodic chemical cleaning are required. Membranes provide a physical separation, but damage to a module could create a pathway through the barrier. Facilities therefore test pressure, flow, and water quality to confirm that the system remains intact. Some recycling systems add reverse osmosis after this stage. Reverse osmosis uses a much tighter barrier and high pressure to remove dissolved salts and many small chemical compounds. It produces a concentrated reject stream that must be managed responsibly. Because reverse osmosis consumes substantial energy, it is selected when the required quality justifies that cost. Physical separation is followed by disinfection. In the system we are examining, treated water passes through a chamber and is exposed to ultraviolet light. The radiation damages genetic material in microorganisms so that they can no longer reproduce effectively. The lamps must deliver a sufficient dose, which depends on intensity, exposure time, and water clarity. Particles can shield microorganisms, so good upstream treatment improves disinfection performance. Operators clean lamp sleeves and replace aging lamps because visible operation does not guarantee the required output. Ozone and chemical disinfectants are alternatives, and some plants combine methods to create further protection. Ultraviolet treatment is effective at the point of exposure, but it leaves no lasting disinfectant in the water. For this reason, a small amount of chlorine may be added before storage or distribution. This residual limits microbial regrowth if the water remains in pipes for an extended period. The dose must be controlled because too little provides inadequate protection, while excessive treatment affects taste, materials, and byproduct formation. The finished water can then enter a covered reservoir. Covering prevents birds, dust, sunlight, and surface runoff from contaminating the treated supply. Storage balances production with demand because the treatment plant may operate steadily while use changes during the day. Reservoir mixing is important. Stagnant zones can lose disinfectant and allow water quality to deteriorate. The distribution network must also be protected from incorrect pipe connections. Where recycled water is not intended for drinking, color-coded pipes, signs, backflow devices, and inspections reduce cross-connection risk. The final part of the system is verification. Continuous monitoring measures variables such as flow, pressure, cloudiness, disinfectant level, and lamp performance. Automatic alarms warn operators when a result moves outside its permitted range. The plant may divert water away from the finished supply until the cause is identified and treatment is restored. Continuous instruments provide immediate information, while laboratory tests check microorganisms and chemicals that cannot be measured reliably every second. Records allow regulators and operators to examine trends rather than respond only to one isolated reading. Quality assurance also includes equipment maintenance, calibration, staff training, emergency plans, and independent review. To conclude, advanced water recycling depends on a sequence of complementary barriers. Preliminary removal protects equipment, settling removes solids, biological treatment consumes dissolved material, and fine barriers improve clarity. Disinfection, protected storage, and continuous verification then maintain the quality achieved by the treatment process.
Today's lecture examines bee pollination as both a biological process and an important part of agricultural production. Many flowering plants depend partly or completely on animals to transfer reproductive material between flowers. Bees are especially effective because they actively collect floral food and often visit many flowers of the same species during one trip. We will first follow what happens during and after a visit, then consider how farming practices influence pollinator communities. A flower must first attract a suitable visitor. Color, shape, scent, temperature, and patterns visible under ultraviolet light can all guide an insect toward the floral center. The flower often provides a reward. One common reward is nectar, a sugar-rich liquid produced in specialized glands. Its concentration and volume vary among plant species and with weather, soil moisture, and time of day. Bees use it as an energy source, and social species may carry part of it back to the colony. Pollen can also provide protein and other nutrients, but it performs a reproductive function for the plant. We need to examine the relevant flower structures. The male structures include filaments supporting pollen-producing organs. When a bee reaches into the flower, its body brushes against the anthers, which release pollen grains. Hair, surface texture, and static electrical charge can help the grains adhere to the insect. A bee may deliberately collect the grains with its legs, yet loose material remains on parts of the body that are difficult to groom. This exposed material is particularly useful to the plant because it can contact the next flower. The bee then moves to another flower, often while continuing to search for the same type of reward. Some grains are transferred from its body to the stigma, the receptive surface of the female flower structure. Successful transfer is more likely when the visitor touches the correct position and the two plants are biologically compatible. Wind, gravity, or self-contact may also move grains in some species, so insect visitation is not the only possible pathway. At this point, pollination has occurred, but the reproductive process is not yet complete. A compatible pollen grain absorbs moisture and begins to grow. It produces a pollen tube that extends down through the style toward an ovule. Chemical signals and tissue structure help guide this growth. The grain remains near the receiving surface while male cells travel within the growing structure. When a male cell reaches the ovule, fertilization can occur. Pollination, therefore, refers to transfer, whereas fertilization refers to the later union of reproductive cells. The distinction is important because transfer can occur without successful reproduction. Incompatible grains, damaged tissue, high temperature, or poor plant condition may interrupt the later stages. Following successful reproduction, the fertilized ovule begins developing into a seed. Hormonal changes also stimulate surrounding flower tissue. In many crop plants, the ovary develops into a fruit that protects seeds and may assist their dispersal. Other flower parts may contribute to the edible structure in crops such as apples or strawberries, so botanical definitions do not always match everyday culinary categories. The amount and pattern of pollen received can affect more than where the development begins. In some crops, inadequate transfer produces smaller, uneven, or poorly shaped harvests because not all ovules develop successfully. More visits are not always better, however, the useful number depends on crop species, visitor efficiency, and conditions during flowering. We can now move from individual flowers to the farming system. Pollination services come from both wild insects and colonies supplied by beekeepers. Wild species vary greatly in body size, nesting behavior, active season, flight distance, and preferred plants. Some nest underground, others use hollow stems or cavities, and only a minority live in large social colonies. Supporting them requires habitat that contains both feeding resources and safe nesting locations. A field may provide abundant flowers for a few weeks but offer little food before or after the crop blooms. Field margins, hedgerows, and cultivated patches, and flowering cover crops can extend the available resources. The value of these areas depends on plant choice, timing, width, management, and connection with other suitable sites. Plant diversity is important because different species flower at different times and provide varying amounts of food. Diversity also supports pollinators with different tongue lengths, body sizes, and seasonal activity. A mixture must be selected carefully to avoid invasive species and to suit local soil and climate. Cutting every margin at once can remove resources suddenly, whereas rotating management leaves some areas available. Nesting conditions require equal attention. Bare, well-drained ground may benefit species that dig nests, while hollow stems and dead would support some cavity nesters. Excessive tidiness can remove these features even when many flowers remain. Chemical exposure creates another challenge. Pesticides include insect control products, fungicides, herbicides, and other substances used to protect production. Risk depends on toxicity, dose, route of contact, timing, formulation, and the species exposed. A product applied while flowers are open may contact visiting insects directly or contaminate pollen and liquid rewards. Spraying when pollinators are inactive, avoiding drift, following label restrictions, and using targeted methods can reduce exposure. Integrated pest management begins with monitoring and uses biological, cultural, physical, and chemical controls in combination. The aim is not to ignore crop damage but to avoid unnecessary treatment and choose the least disruptive effective response. Communication between growers and beekeepers is also necessary when colonies are placed near treated fields. Large areas of crops that bloom for a short period may require more visitors than the surrounding landscape can provide at that moment. Farmers may therefore rent commercially managed honeybee colonies and position hives near the crop during flowering. Managed colonies can be moved and inspected, and their numbers can be estimated more easily than wild populations. They are not a complete replacement for wild pollinators. Different insects work under different temperatures, visit different flower shapes, and transfer material with varying efficiency. A diverse community can provide greater stability when weather or disease reduces the activity of one group. Hive placement also requires planning. Too few colonies may limit visits, while excessive concentration can increase competition for food and disease transmission. Water, shade, vehicle access, wind protection, and distance from chemical application all influence a suitable location. Researchers measure pollination using several methods. They may count visits, identify visitor species, compare open flowers with flowers protected by mesh, or add pollen by hand. Counting visits alone can be misleading because one visitor may transfer much more material per visit than another. Final measurements can include seed number, shape, weight, quality, and economic value. Studies should be repeated across fields and seasons because weather and surrounding land use can change the result. To conclude, bee pollination is a sequence linking flower attraction, material transfer, cell union, and crop development. Agricultural support must also operate as a system, combining habitat, diverse food, nesting sites, careful chemical use, and appropriate colony management. Protecting one stage while neglecting another may leave the complete process vulnerable.
Today's lecture explains how an online learning system supports a learner from initial access to the final course outcome. Online education is not simply a collection of videos placed on a website. It combines user accounts, organized content, communication tools, assessment, support services, data systems, and academic rules. Institutions choose different technologies, but the underlying functions are often similar. We will follow one learner through the system and examine what happens at each stage. The first step is creating a user account. The learner provides basic information, chooses login credentials, and confirms an email address or another contact method. Registration alone does not necessarily give access to a specific course. The learner must also complete enrollment, which formally connects the account with the selected course or program. Enrollment may follow payment, institutional approval, prerequisite checking, or automatic assignment by an employer. The system records the start date, expected duration, study mode, and any access restrictions. If a learner changes course, the account may remain active while the course relationship is updated. The next function concerns identity and security. Authentication is the process used to confirm that the person requesting access is linked to the stated account. A password is the most familiar method, but stronger systems may add a temporary code, security key, or biometric check. Using two different forms of evidence reduces the risk created by a stolen password. Identity controls must be strong enough to protect records without creating unnecessary barriers for legitimate learners. Password recovery and account support are therefore part of the complete system. After successful login, the learner usually arrives at a personal dashboard. This screen displays active courses, upcoming deadlines, announcements, recent messages, and a summary of progress. It differs from a public catalog, which advertises courses that may be available, but does not show the learner's current work. A well-designed dashboard prioritizes urgent information without presenting so many alerts that important tasks are hidden. Links should behave consistently so that learners do not spend excessive effort searching for basic functions. The learner then enters the course space. Content is commonly divided into modules, with each unit focusing on a topic, week, skill, or stage of a project. A module may contain an introduction, reading, video, practical activity, discussion, quiz, and summary. Clear sequence markers show which activities are required, which are optional, and what should be completed first. Some systems release every unit at the beginning, while others open material according to dates or previous results. Requiring successful work before the next unit opens is sometimes called conditional release. This approach can guide progression, but an unnecessary restriction may prevent learners from planning ahead. Online activity can be classified according to timing. Synchronous learning requires participants to attend at the same time, even when they are in different locations. Examples include live video classes, real-time tutorials, oral examinations, and scheduled group meetings. Immediate questions and social presence are advantages, but time zones, employment, caring duties, and internet quality can limit attendance. A live session should therefore have a clear purpose rather than simply copy a long classroom lecture onto a video call. Asynchronous activity does not require everyone to participate simultaneously. Recorded explanations, readings, self-paced exercises, email, and discussion boards are common examples. Learners gain flexibility and time to reflect, but delayed communication can slow clarification and reduce a sense of connection. Effective courses often combine both forms, instead of treating them as competing systems. A recorded explanation may introduce a concept, a discussion may allow reflection, and a short live meeting may address complex questions. Assessment is another major component. An online quiz can mark fixed responses automatically and provide an immediate result. Essays, designs, demonstrations, and spoken tasks usually require human judgment or a carefully designed rubric. Randomized questions and time limits can reduce simple answer sharing, but they do not guarantee academic integrity. Assessment should match the intended skill. A multiple-choice test cannot fully demonstrate every kind of practical or creative ability. The platform records many events as learners work. Learning analytics use activity data to identify patterns in login frequency, resource use, submission timing, quiz attempts, and progress. A tutor might notice that many learners stop at the same page or repeatedly miss one concept. That pattern can indicate confusing instructions, difficult content, a technical failure, or an unrealistic deadline. Data do not explain the cause automatically, so staff must investigate before deciding on an intervention. A learner who has not logged in may be disengaged, but may instead lack internet access, or be studying downloaded material offline. Institutions must also be transparent about which data are collected, how long they are kept, and who can see them. We can now consider response to learner work. Useful feedback identifies what was successful, explains an error, and suggests a practical next step. A numerical score alone can show performance without showing how to improve it. Automatic response works well for some predictable errors, while complex reasoning usually needs a tutor's explanation. Timing matters, because a response received after the next task may arrive too late to influence it. Learners also need an opportunity to apply the advice rather than merely read it. Peer review can expose learners to alternative approaches, but it requires clear criteria and respectful communication. A functioning platform must be usable by people with different needs and technologies. Digital accessibility means designing content and controls so that disability does not create an avoidable barrier. Captions support people who cannot hear the audio and also help learners studying in a noisy environment or an additional language. Images need meaningful text alternatives when their content is important. Keyboard navigation allows a user to operate controls without depending on a mouse or touch screen. Color should not be the only method used to communicate status, and text must remain readable when enlarged. Accessibility should be built into templates and production methods rather than added only after a complaint. Technical support addresses a related but different set of problems. Help pages, device checks, contact routes, and clear error messages allow learners to recover when something fails. Academic support may include tutoring, library access, study guidance, and contact with teaching staff. At the final stage, the system checks whether required conditions have been met. Course completion may depend on viewing essential material, submitting assignments, reaching a minimum score, attending required sessions, or completing a final project. Completion is not identical to passing one assessment, because several conditions may contribute to the course outcome. Once the rules are satisfied, the platform may issue a certificate, update an institutional record, or unlock the next course. Staff should be able to correct exceptional cases when a technical failure or approved adjustment affects the automatic record. To conclude, Online learning works through an interconnected sequence rather than one isolated tool. Access and identity lead to organized activities, interaction, assessment, data interpretation, feedback, and support. The system succeeds only when technology, teaching design, accessibility, and academic policy operate together.
Today's lecture explains how a grid-connected battery storage system receives, stores, and returns electrical energy. We will examine the path through the equipment, the processes inside the cells, and the controls required for reliable operation. Although several battery chemistries are available, the example will use a rechargeable lithium-ion installation. The same broad system functions apply to many large installations, even when materials and operating limits differ. Storage does not generate new energy, it shifts available energy from one time to another. Let us begin with the decision to charge. At certain times, electricity production is greater than immediate consumption. This surplus may result from strong wind, bright sunlight, low demand, or an operating generator that cannot change output quickly. A control center can instruct the storage plant to absorb part of the excess rather than reduce generation or overload the network. The instruction considers market prices, network limits, expected demand, and the battery's present condition. Charging is not automatically useful whenever supply is high. The plant must retain enough space and remain within safe limits. Electricity arriving from the grid normally changes direction many times each second. Battery cells cannot store this alternating form without conversion. Power electronics first convert the incoming electricity into direct current, in which charge flows with one overall direction. The equipment controls voltage and current so that the cells receive an acceptable charging rate. Conversion produces some heat, so efficiency is below 100%. A transformer may also change voltage, but changing voltage is not the same function as changing current form. We can now look inside a cell. Each cell contains two electrodes separated physically but connected by an ion-conducting medium. During charging, charged particles move between the electrodes through the electrolyte. A separator prevents the electrodes from touching while allowing this internal movement. If the separator is damaged, an internal short circuit can create rapid heating. Electrode materials accept or release the moving particles according to reversible reactions. The supplied electrical energy is thereby stored in chemical form within the cell materials. Stored energy is not simply electricity waiting unchanged inside a container. Charging alters the chemical state of the electrodes. The reaction cannot proceed without limits. Excessive voltage can damage materials, while a very high charging rate can produce unwanted deposits and additional heat. Cells are therefore grouped into modules and larger packs with electrical and mechanical protection. When the network requires energy, the sequence reverses. Charged particles move back through the cell as the chemical reaction releases stored energy. Electrons cannot pass through the separator, so they travel through the external circuit and perform useful electrical work. Their movement creates direct current at the battery terminals. It is important not to confuse electrons in the external wires with ions moving inside the cell. Both movements are parts of the same reaction, but they follow different paths. Grid equipment and most connected loads require alternating current. An inverter converts the direct output into alternating current with the required frequency and waveform. Modern units can respond within fractions of a second and may also support voltage or frequency control. A transformer then matches the output voltage to the connection point. Protective switches isolate the plant if measurements indicate a dangerous fault. Energy is lost in the cells, cables, conversion equipment, and cooling system during a complete cycle. Round-trip efficiency compares the energy returned with the energy used to charge the plant. It should be measured under stated conditions because losses change with power level, weather, and auxiliary equipment. Thermal control is especially important. Electrochemical reactions and electrical resistance produce heat during both charging and discharge. Cooling equipment controls battery temperature and reduces differences between neighboring cells. Systems may use forced air, liquid loops, or refrigerant depending on size, climate, and design. Very low conditions can also reduce performance, so some installations require heating before rapid charging. Uneven conditions cause cells to age at different rates and make the complete pack harder to use efficiently. Sensors are positioned throughout modules, containers, conversion equipment, and cooling circuits. System monitoring checks voltage, current, temperature, insulation, airflow, and communication status. A battery management system compares individual cells and estimates how much energy can be accepted or delivered safely. If one cell approaches a limit before the others, the complete pack may need to reduce its operating range. Balancing circuits help bring cell states closer together, although they cannot repair physical damage. Alarms can trigger a reduced power mode, controlled shutdown, or emergency isolation. Fire detection and suppression add further layers, and equipment spacing can limit the spread of an incident. Operating records are also used to investigate faults and improve future control decisions. Battery performance changes with time and use. Calendar aging occurs even when the plant is not cycling, and it generally increases at high charge levels and high temperatures. Cycle aging results from repeated charging and discharge, particularly under demanding rates or deep operating ranges. These processes gradually reduce usable capacity, meaning the battery holds less energy than when it was new. Internal resistance may also rise, limiting power and increasing heat at a given current. Power and capacity are related but distinct, one describes rate, and the other describes amount. Operators can extend service life by controlling temperature, avoiding unnecessary extremes, and selecting an operating range suited to the task. A battery used for short frequency support may experience different stress from one charge by solar energy each day. End of service in one application does not always mean immediate disposal. A pack that no longer meets demanding vehicle or grid requirements may still serve a lower power stationary use after careful testing. This second life approach delays material processing, but safety history and remaining performance must be known. Eventually, recycling can recover metals and other materials for use in new products. Packs must first be discharged, transported safely, identified, and dismantled or processed under controlled conditions. Mechanical treatment can separate physical fractions, while thermal or chemical methods recover particular compounds. Recovery rates differ by material and process, and economic value does not always match environmental importance. Product design can improve future recovery by reducing unnecessary adhesives, clarifying chemistry, and allowing safer disassembly. Recycling does not eliminate the impacts of mining or manufacturing, but it can reduce demand for newly extracted material. To conclude, battery storage is an integrated electrical, chemical, thermal, and digital system. Successful operation requires controlled conversion, safe cell reactions, rapid protection, appropriate temperature, and accurate supervision. Long-term value also depends on managing aging and planning for reuse or material recovery from the beginning.
Today we will examine how museums preserve physical objects for research, education, and public display. Preservation involves more than repairing visible damage after it has occurred. It combines careful treatment with preventive measures that slow future deterioration. The correct method depends on the object's materials, construction, history, and intended use. A metal tool, a painted wooden panel, and a silk costume cannot be treated as though they react in the same way. Our first topic is the sequence followed when an object enters a conservation laboratory. Registration confirms identity and ownership, but it does not describe every crack, stain, or unstable area. Before any intervention, a conservator completes a condition assessment that records the object's present physical state. This document notes earlier repairs, missing components, signs of deterioration, and locations where the structure appears weak. Measurements may be added, and unusual features are marked on a simple drawing. The record protects both the institution and the object because later changes can be compared with a reliable starting point. Written descriptions are essential, although words alone cannot show the exact shape or position of every feature. For that reason, conservators create a visual record through photography before moving or cleaning the object. Images are taken from several angles under consistent lighting, with a scale and identification label visible. Additional images may be made during treatment, allowing each intervention to be traced rather than guessed afterward. Once documentation is complete, the conservator considers whether surface cleaning is both useful and safe. Cleaning is not an attempt to make every historical object appear new. The first practical step is often to remove loose dust using a soft brush directed toward a low-powered vacuum. The brush loosens particles, while a fine screen prevents detached fragments from disappearing into the machine. Strong suction would be faster, but it could lift paint, fibers, or decorative pieces from a fragile surface. Some material that looks dirty may actually be evidence of use, manufacture, or age and should remain untouched. If dry cleaning is insufficient, a liquid method may be considered, but this introduces additional risk. Water is not automatically harmless because it can swell wood, move color, or react with salts. The conservator therefore studies the material and chooses a solvent capable of removing the unwanted substance without attacking the object. Even a carefully chosen liquid is first tested on a small hidden area, rather than applied across the whole surface. The test reveals whether color transfers, gloss changes, or the surface becomes softer. Treatment proceeds gradually, and used swabs are checked for any sign that historic material is being removed. After cleaning, attention shifts to structural weakness. A temporary support can hold an unstable piece during work, but it is not necessarily part of the completed repair. Where a fragment is loose or a layer is lifting, the conservator may introduce a small amount of reversible adhesive. Reversibility matters because a future specialist may need to remove the repair without causing further damage. More material does not produce a stronger result. Excess can stain a surface and make later work difficult. Gaps are sometimes filled to support surrounding material, although missing areas are not always reconstructed. Decisions depend on structural need, available evidence, and the ethical policy of the institution. Once the object is stable, the final surface treatment is considered. A storage box or transport package offers physical protection, but neither becomes part of the object itself. In selected cases, a thin protective coating is applied to reduce contact with moisture, pollutants, or handling. Such a layer must be compatible with the surface and should not create an unnatural appearance. It is not used automatically, since a poorly chosen layer may yellow, trap harmful substances, or become difficult to remove. We have now followed active treatment from examination to stabilization. However, laboratory work has limited value if the object returns to a damaging environment. Preventive conservation aims to manage that environment and reduce the need for future repair. Temperature is commonly measured, but many museum materials respond particularly strongly to the amount of moisture in the air. Wood, paper, leather, and textiles absorb and release moisture as surrounding conditions change. Stable humidity therefore reduces repeated expansion and shrinkage, while also limiting corrosion and biological growth. Stability is often more important than attempting to maintain one perfect number in every room. Rapid fluctuations can place stress on join materials because each component may react at a different rate. Light creates another difficulty because the damage it causes is cumulative and cannot be reversed. Visible illumination allows visitors to see an object, yet its intensity and duration still require control. Window films and display case filters are especially useful for reducing ultraviolet radiation, which human eyes cannot see. Sensitive dyes, paper, and photographs may fade or weaken, even when no immediate change is obvious. Staff therefore measure exposure over time, rather than relying only on how bright a gallery appears. Biological threats must also be identified before widespread damage develops. Food, nesting material, and uncontrolled entry points can attract pests to storage and display areas. Small monitoring traps placed in fixed locations help staff discover whether insects are present and where activity is concentrated. The traps are inspected on a schedule, and findings are recorded by species, number, date, and location. A trap is a detection tool rather than a complete solution, so staff must also improve cleaning, sealing, and storage practices. Chemical treatment is considered cautiously because it may endanger people or react with collection materials. Finally, museums control the total time for which vulnerable objects are exposed to display conditions. Closing a gallery earlier would reduce access for everyone, but would not distribute exposure sensibly across a collection. Instead, planned rotation allows one object to rest in controlled storage, while another takes its place in the exhibition. This approach is especially valuable for works on paper, costumes, photographs, and other light-sensitive materials. Curators must coordinate the change carefully so that the exhibition remains coherent and replacement objects are suitable. Accurate records ensure that no vulnerable item remains on view simply because its permitted period was forgotten. To conclude, successful preservation begins with evidence, proceeds through minimal and carefully tested treatment, and continues through environmental management. Documentation, cleaning, stabilization, and surface protection each have a distinct purpose within the treatment sequence. Environmental stability, light control, pest detection, and limited display periods then slow further deterioration. The central principle is not to make an object look new, but to preserve its material evidence with the least harmful intervention.